I'm Rotong Yu. It's a great honor to present our work on in-depth analyze on adoption of attack mitigations in embedded devices. So in this talk, I'd like to briefly introduce the research questions we are trying to answer in the NDSS paper, Building Embedded Systems back in 1996. So I also would like to introduce the challenges when we're performing such a large-scale analysis on embedded devices. In the meanwhile, I'd like to discuss how we solve those challenges and what we have borrowed from the previous work and what we have concluded, the result we have finding from the experiment. So this work has been done in collaboration between Stevens Institute of Technology, University of Utah, University of Puglia, Norwegian University of Science and Technology, Delft University, and CyberITL Independent Research Group. So let's get started. So embedded devices are running everywhere to connect the physical world with the digital world. By estimation, there are more than 35 million embedded devices installed in the wild. This large-scale deployment makes the security of embedded devices critical. So, in fact, many mitigations are used to protect the desktop systems from different kinds of attacks. These memory-related mitigations include both user space and kernel level. Here, I listed some of the most famous ones, including the stack canary, non-executable stack, address space layout randomization, and so on. So these mitigations used by the desktop binaries can also be applied to the embedded systems. However, we have some preliminary result from our collaborators which indicate the fact mitigations is rarely adopted on embedded devices. So if you're looking at this table, we presented the result from our collaborator by evaluating the mitigations in popular routers. So looking at this table, we can see the binaries from Ubuntu desktop are well protected with canary, non-executable stack, and relocation rate only. But in comparison, all the mitigations are almost completely missing in the embedded devices. So this observation motivated us to extend this study into a much larger scale because our collaborator only evaluated like 28 popular routers. But as we know, we have much more embedded devices running on the wild, routers, access point, or network switch, and so on. So this motivated us to extend this study. What is the count? What do you mean by the count is the number of binaries they are trying to evaluate, the number of the ELF binary. Thank you. So in this paper, we in the NDSS paper, we mainly focus on three research questions. The first one is, do embedded devices adopt attack mitigations? And the second one is the adoption of attack mitigations improving over time. This is a very concerned question because, if the situation is not getting better, then it won't improve forever. So the third question is, if the mitigations are missing, what are the possible reasons? So to answer all these three questions, we would like to perform a large-scale study on evaluating the mitigation adoption on embedded devices. So our study focuses on the Linux-based devices. We focus on the Linux-based devices because this is the most dominant type of the embedded devices, and it's also support most of these mitigations. So if it doesn't support the mitigation, then there is no way we can evaluate it. So before we discuss how we answer these questions and what are the conclusions we have, I'd like to briefly talk about the challenges we have when performing such a large-scale study. So the first one is to building a high-quality data set. This is challenging because, there are previous data set are valuable or published, but they are outdated, and some of them are even invalid today. So the second challenge is to unpacking those firmware images. Usually, the vendors will publish their firmware images in different formats. So those diversity of those firmware will make the unpacking process to be more complicated. If you didn't properly handle it, you won't be able to recover the whole information. And the third is to accurately identifying the attack mitigations. There are existing tools to performing such tasks, like checksag or many others. So they focus on the user space mitigations usually. So they didn't consider the kernel-level mitigation, and sometimes they didn't do well on the user space mitigation identification because they failed to consider the corner cases. I would like to discuss that in the next few slides. So all these challenges makes our work much more valuable, I think. So I would like to also discuss how we solve each of these challenges. So the design of our study is quite straightforward, which has 4 major components. The first stage is to collecting the firmware images using web crawler. So the web crawler is designed based on the previous work. This is so we're only collecting the firmwares publicly available for ethical consideration. We will not try to dig into the private data or getting some private sources from the vendor. This is the safest way we can do. So after the data has been collected, the next step is to unpacking those firmwares. We will try to extract both the file systems and the Linux kernels. Like I mentioned, we focus on the Linux-based devices, so it's only Linux kernel. So once we have all those informations collected, the next step is to identify those attack mitigations, and finally is just summarizing all the results we have. So first, I'd like to discuss how we solve the challenges when collecting a very representative data set. So what we do is we try to reuse the data set from previous research, but unfortunately, these data sets are not, most of them are invalid today. For instance, we tried over 20,000 URLs provided by a paper, a large-scale analysis of security of embedded firmware from Usenix Security 2014. But we only have like 5% of these URLs are valid. And in fact, 5% of them, that doesn't mean all of them are like the real firmwares, because they have some many other like manuals or text files included in those URLs. So I think I think only like half of them are the real firmware, so most of them are just invalid. We also try to reuse the web crawler designed by another NDSS paper from Adney. This is a paper from NDSS 2016. They use the web crawler to collecting many firmwares from different vendor websites. But when we are trying to reuse their web crawler, most of them are just outdated. I think they didn't maintain the web crawler recently. So the vendor website are changing all the time. So if you didn't properly handle that, the web crawlers are no longer available. So what we did is we decided to update the web crawler based on from Adney. I think there are 2 major benefits of doing so. The first is they provided a very good framework to begin with, and second, the web crawler only consider the publicly available firmware. This is what we want. We don't want to dig into the private data or get trouble into the ethical consideration. That's why we decided to update all the firmware, all the web crawlers from the previous NDSS paper. So in total, we collected over 18,000 firmware images from 38 popular vendors. These firmware images range from 1998 to 2021, which contains most common types of embedded devices. And also the number of images we collected is comparable with all the previous large-scale studies. So once the firmware images are collected, the next step is to unpack the firmware images. So I'd like to discuss the challenges when performing the unpacking process. So as we can see, a firmware image is usually composed with many different components, including the bootloader, the kernel, and the file system and the data. So unpack the firmware image. We used a firmware unpacking tool from the previous work, the same one in the NDSS paper. So the tool is designed based on bin work and is capable of extracting both file system and the Linux kernel. This is very good because the kernel itself can be analyzed, and the ELF binaries are the evaluating target included in the file systems. So it can perform both. It can extract both the file system and the Linux kernel, which matches our purpose. So that's why we decided to reuse it. And also, bin work is one of the state-of-art tool on unpacking the firmware image. So I think unpacking firmware image is still an open research question, because bin work is basically based on signature match strategy. They will find the signature of the file system, and that's how they identify the file system. But during our experiment, we have more findings, like sometimes the firmware itself is just not containing the file systems. They have some binaries packaged in a different way. So that's why we have so many examples of unsuccessful unpacking by using the firm-adni or the bin work. So during the extraction stage, or when we are trying to extract the file system, we will search for the standard directories like bin or sbin, lib, and etc. Under the root directory. So this is the way to help us identify the real file systems. Like I said, there may have multiple file systems in the firmware. Some of them are just random stuff. So we are trying to setting a filter on the directories, so we can have the real file system, which including most of the ELF binaries to be evaluated. So once we have the directories, we will then recursively going through all those files inside the directory, and we will extract all of them recursively. These binaries will be evaluated. So extracting the Linux kernel is a little bit more complicated, because the firmware extraction tool is able to extract the Linux kernel, but the extracted stuff is in a raw data block. So to recover more information of the Linux kernel, we will do two more things. The first is to recursively extract the content in the raw format Linux kernel. In this way, we will be able to find the configuration files. Sometimes the configuration files is just unpacked as part of the binary blob of the Linux kernel. So doing so, we are able to recover or identify the configuration file, which is very helpful for our further Linux kernel analyze. And the other thing we did is we used another tool which is called VM Linux to ELF. This is a tool which is able to convert the raw binary blob into a fully analyzable ELF binary. So this tool is able to recover the Linux kernel into ELF format with all the symbols recovered. The symbols will be very helpful for us to analyze the Linux kernel, and I will discuss that in the next following slides. So we will see firmware is successfully unpacked if at least a file system or a Linux kernel is extracted. So this table presented the number of images we collected and unpacked for each vendor. So in among of the 18,000 firmware images we collected, we can successfully unpack 10,000 of them, which is about 59% success rate. This result also include over 9,000 file systems with 3 million ELF binaries inside, and also 8,000 Linux kernels. So in among of these 8,000 Linux kernels, we found 558 of them are containing the configuration file, and more than 3,000 of them can be converted into the ELF format. So now I would like to introduce how we select the mitigations we put into consideration. So the first is user space mitigation. We included all the mitigations that are active on the modern Linux distribution. This is also the same selection for all the previous popular mitigation identification tools. So the mitigations including the stack canary, fortified source, precision independent code, relocation read only, and non-executable stack. I will also explain the improvement we have been made when we are trying to identify those attack mitigations. So the general approach of identifying those mitigations are very useful, but it needs to be improved, especially on the following three: stack canary, fortified source, and relocation rate only. So the general approach of detecting stack canary is just searching for the indicator function, which is stack check file. This is a very efficient way for dynamically linked binaries, because the stack check file is just there in the symbol. So if it's a dynamically linked library, you can just search for that indicator function. This is totally fine. But for statically linked binary, this is a different story, because sometimes you just don't know whether it's being used or not, or maybe the same function can be named in a different way. So you won't be able to always rely on the indicator function. So what we are doing here is we will try to search for the error message, which is the stack smashing detected. So we notice that this error message it keeps constant for all the binaries, no matter what is the architecture or what is the optimization level. So it keeps the same. So what we can do is we will disassemble the statically linked library binary, and we search for the error message, so we can identify which function has been is using that string or that error message, and then we will see what is the reference of this function. So if the function has been actually referenced, then we know, okay, this stack check file function is actually being called. So we know the binary is protected with stack canary. So the fortified source can be used in a similar way, but the error message is a little bit different, which is buffer overflow detected. So it's the same for dynamically linked binary. We don't need to do any extra things, but for statically linked binary, we will search for the error message and do the disassembly. So another improvement we did is the relocation rate only. So the The previous approach is just looking at the permission flags of the GOT section, and we just noticed the previous two, they ignore the permission flag of the GOT PLT section, which is also part of the indicator of the relocation rate only. If it's a full protection of the rate only, relocation rate only, the two sections will be merged into one. But if it's a partial, then the GOT PLT section should be marked as readable, because this section need to save the information. So this is how we improve the traditional way of the user space mitigation identification. And also we are following a similar rules on selecting the kernel level mitigations. So first, the mitigation should be active in the Linux distribution. And second, it has been released over 3 years, so the vendors have enough time to deploy them. And finally, it's applicable to the embedded systems. So the way we identifying those kernel level mitigation, we have 3 major informations can be used. The first is the Linux kernel version. So we know if assuming we have some mitigations which is released after imagine the version like 2.6 or something, then we know all the kernels before that version won't be able to adopt it. So the second thing we can use is the configuration file. So the configuration file provided the most detailed informations. So if the attack mitigation is marked as yes in the configuration file, then we know it's definitely enabled. But if the configuration file is missing, then we have to try to recover that Linux kernel into a L format. In that way, as I said, the tool is able to recover all the informations in the symbol. If we have the information in the symbol, what we can do is similar to the detection of stack canary. We can use the indicator functions to decide whether the attack mitigations are enabled or not. For example, the stack check file again can be used for the kernel to use as the indicator function for stack protector. So this is the 3 major informations we are used for kernel level mitigation identification. As far as we know, all the previous mitigation identification tools, they don't do the kernel level mitigation identification, which is like a gap we are trying to fill in. So right now we have discussed the challenges and how we solve these challenges. Now I would like to talk about the experiment we have been conducted to answer the research questions we previously proposed. Remember, the first one is the attack mitigations are actually adopted by the embedded devices. So to answer this question, what we do is we measure the mitigation adoption rate for all the Linux it's just sorry, the slides is keep going itself. It's my fault. So again, going back to the first research question, is about is the embedded devices are well protected with the mitigations. So what we do is we measure the mitigation adoption for all the embedded binaries, and also we are trying to break down the result, by splitting the binaries by the types. For example, the type of the device, the type of the binary, is it dynamic link or is it static link, and also where the binaries are coming from. Imagine the vendors or the type of the devices. So in this way we can categorize those binaries, and then we can find more interesting answers. And the second question is it changing over time? To do that, we keep track of the mitigation change over the time in both user space and kernel level. And also what we also did is we keep track of the evaluation of individual firmware, which means imagine we have some firmwares from the same product. We will compare the oldest version versus the newest version, and we will see if the newest version is doing better or not. So the last question is, what are the potential reasons of such missing mitigations? To answer this question, we didn't directly contact with the vendors, and we don't have that power to do so. So what we did is just using all the data we have, and we do some evaluation based on these data. So the first thing we do is we notice many of the firmwares are built based on the building tools. So we will see the limitations of those building tools. If the building tools is not enable those mitigations by itself, then the vendors won't be able to use it. And the second thing we do is we try to evaluate the reused batteries. Batteries are reused between the vendors and also between the products. So if those reused batteries are not well protected, then this missing of mitigation will easily spread to many more devices. And third, what we do is we measure the mitigation overhead, because sometimes the vendors are willing to use it, but they're just not affordable. If assuming applying the stack canary will slow down your rotor like 20%, maybe the user or the vendor themselves will think this is not affordable. So the last question is whether this missing of mitigation attributed to the missing of the embedded vulnerabilities. So imagine if there is no vulnerabilities or there is no attacks, then why should we defense or batteries? So we will perform a case study to answer this question as well. So we will the experiment for our kernel-level study is quite similar. We measure the mitigation adoption rate for all the Linux kernel to answer the first question, and also we will keep track of the mitigation change over time on the kernel as well. But the only mitigation we try to keep track is stack protector, because all the other mitigations are rarely adopted. So keep tracking of 0 doesn't make any sense. So stack protector is the only one we will focus on. So here I'd like to talk about the findings to answer the questions we have been proposed. So the first one is embedded devices adopt attack mitigations. The answer to this question is no, because if you're looking at this table, on average, the adoption rate of all the mitigations for embedded devices are surprisingly low, especially comparing with the desktop batteries. And also, if we break down those batteries by the vendors, we will see the result vary largely across the vendors. Some good performance vendors will have like 85% adoption rate on the stack canary, but the bad ones will completely ignore it. So we have a little bit more interesting result by breaking down the batteries by type. Here I would like to share one of them, which is breaking down the battery by the architecture. So if we're looking at this diagram or this figure, we can see ARM as the largest group has the moderate mitigation adoption rate on almost all the attack mitigations. But the MIPS as the second largest group has the lower-least adoption rate in nearly every mitigations. So in general, x86 and ARM64 batteries have a relatively higher adoption rate because those batteries are usually running in a newly built environment. So the adoption in kernel-level mitigation is also disappointing. Like I mentioned, we only keep track of the stack protector because this is the only one commonly exists in the Linux kernel. So in among of the over 3,000 Linux kernel we analyzed, only 159 of them are protected with the stack protector. This is like less than 2%, I think. So the other protections are almost completely missing. So the evidence indicates that kernel-level mitigation are rarely adopted. So the answer for the second question is that so the second question is if the attack mitigations are actually improving over time. So if you're looking at this figure, you will have the answer. So the only one present a constantly positive trend is non-executable stack. So all the other mitigations are not improving, and some of them are even getting worse. Like I said, we also have experiments by comparing the newest version of a firmware versus the oldest version. So in this figure, you can see most of the firmwares are not changing at all, the green ones, and some of them are getting better, the red ones, and more of them are getting even worse, the blue ones. Okay. So we also have the experiment for the kernel level to mitigation findings to answer Q2. So we only keep track of the change of stack protector because this is the only one consistently commonly exists in the wild. But the good thing is that looking at this figure, we can see in the past decade, the adoption of stack protector is constantly increasing. I think the most important reason for that is many of the vendors are actually using the newer version of Linux kernel, which brings the positive trend. So to answer the last question, what is the possible reasons of missing mitigations? The first thing we do is we try to understand the limitation of the building tools. So build root is one of them, the most popular one. So looking at this table, we can see many of the mitigations are not available on build root before 2012, which means if you use build root before 2012, you won't be able to enable those mitigations. So many more mitigations are available after 2017. But if the vendor didn't properly or didn't update their building tools in time, they won't be able to use it for their devices. So another reason for the missing of mitigation comes from the large reuse of binaries. As I said, the binary reuse happens between the product and across the vendors. So the left table is indicating the number of individual or of unique binaries in each of the vendor. So on average, only 9% of the binaries are unique in the vendor, which means the vendors are borrow the binaries from one product to the other. Yes. Oh, okay. So going back, the red table, the red figure is indicating the heat map, which indicate the binary use across the vendor. So the darker color means a large number of binaries. So we can see the binary reuse across the vendor are also very common. So if those reused binaries are not well protected, this missing of mitigation will be easily spread to many more devices. So the last one is the potential. The other experiment we have is to measuring the overhead, right? So here we can see some of the overhead is observable, like the stack canary, PI precision independent code, and relocation rate only. But like I said, we don't know if this is affordable or not. This needs to be confirmed by the vendor. So another question is the missing of mitigation attribute to the missing of the embedded vulnerabilities? So the answer for this question is also no, because we have a case study which indicate that there are many memory-related vulnerabilities reported recently on 2021, the time we conduct our experiment, which affected millions of devices. But if we're looking into those vulnerable binaries, we will see the attack mitigation is not improving at all, and even getting worse on average. So next, I would like to generally talk about some research questions, or the way we design our study. So the first one is how the previous research motivated us. Obviously, as I mentioned, our experiment is beginning by trying to reuse the previous data set and also use the previously designed web crawler. So this is the starting point. So we decided to extend one of the web crawler because I think the implementing based on the others' work is a very efficient way. And also we try to reuse the state-of-art firmware unpacking tool. So the second one is any intermediate result. The answer is yes. So first, we have all the firmware images, the file systems, and the Linux kernel extracted. All those are like raw data, which can be considered as an intermediate result. But we have more intermediate result by evaluating the attack mitigations. So we will keep another file, keeps all the statics result of the mitigation identification of a binary from the same product. So this is the way we manage the static result. Like I said, we have more than 3 million ELF binaries, so you need to organize them in a proper way. Otherwise, everything is in a mess. So the third, do we share the data? The answer is yes. We will share all the data we collected and used during the research, but we will not directly share the firmware image itself. Instead, we will give you the links. This is for ethical consideration again. We don't redistribute the data. We don't have the permission from the vendors. And again, we don't, like I said, we don't report any of these findings to the vendors, and we didn't directly contact with them. So this is also the reason we didn't have the permission to directly redistribute any of the data. So at the very end, I'd like to discuss some of the limitations. As we know, none of the paper is perfect, so do ours. So the first one is the imbalance of the data set. If you're looking at the tables, you will see some of the mitigations. Some of the data from some of the vendors are less. The others vendors will have more. So this imbalance of data set will bring some overhead. Not overhead. Maybe there will be overfitting in our data set. Maybe sometimes the results are just reflecting the dominant vendors. The others will be ignored. So the other thing is the reliability of the mitigation identification. So the problem here is that we assuming all the binaries are not encrypted or obfuscated. So if doing so, I think our approach will not be accurate anymore. Especially some of the approach we used are trying to search the string, the error message. Imagine if the vendors are protecting their firmwares, by hiding those informations, we won't be able to accurately identify the attack mitigations anymore.